Hey everybody, this is Tom Cherryholmes with Errata Online and the FujiNet project. And I wanted to make a video showing here some of the internals of what I'm building for the end device, and specifically the test programs that I am having to write to test out the individual pieces of functionality for the SIO layer of the end device. This is actually important because there are two individual layers here at work before you ever get to the user-facing side of all of this. The FujiNet side only deals in SIO. It deals in individual commands in which the size and the nature of the data that's sent to and from the device and the computer is already known beforehand, and you deal with things in very block-sized pieces. So you think of them as packets going back and forth between the FujiNet and the Atari, each with a specific purpose in mind. Things like opening a connection, closing a connection, reading from a connection, writing to a connection, etc. Individual atomic commands that have to be handled at that level. And more importantly, when something goes wrong, such as a connection not able to be established or a connection dropping, that needs to actually be handled at this level too and appropriately reported up as an error so that the CIO handler can pass that all the way back to the user. We start by looking at what is essentially the highest level piece on the ESP side, which is the network CPP class. And if we actually take a look, it's broken up into a handful of individual SIO commands. Since this is a subclass of the SIO device, it actually inherits a lot of functionality that the other SIO devices in FujiNet also use. So that all we need to do is implement the bits and pieces that are different for our particular device. You can see some familiar commands here, such as reading and writing and status. And you see a special case for commands that don't exactly fall into this particular trap here. But you also see some commands for opening and closing connections. This is absolutely important because all of the protocol-specific aspects are actually handled via the FujiNet itself. Let me get this out of the way for just a moment. So that means essentially all of the business of setting up the connection, choosing the right protocol, and exposing a nice clean interface to the Atari is all handled by the FujiNet itself. And so because of that, we need explicit commands for opening and closing connections that you don't see on other SIO devices, because we're needing to set up additional state before the read and write commands and the status commands actually make any sense. With that, if we dig into each one of these, we'll kind of go over these relatively quickly just from a high-level perspective. We can see the open command, whose whole purpose in life here is to grab a device specification, parse that device specification, figure out if it's valid or not, and either pass back an error indicating if it's not a valid device specification or not, allocate the buffers that we need, open the protocol. If we can't, then we send back an error appropriately. Now you'll see a common pattern inside of network CPP here that's repeated over and over again. And that's that we're taking one of the status buffer bytes and we're using it, the very last one as a matter of fact, and using it as an error. In traditional Atari fashion, we have a status request, and a status request will send back 4 bytes that get put into dvstat for us. And the OS actually sets aside that little chunk of memory specifically for this purpose. So we've fit our status request to fit within that area, a little area of memory. Because it's there for us, why not use it? And for that, we've allocated 2 bytes for the receive buffer length, which ostensibly means that you can have up to 65,535 bytes waiting to be dealt with. I wouldn't recommend reading or writing that amount of memory, because writing a request that large, for 2 reasons. Namely because if you're reading that much, you're gonna run out of memory long before you ever hit that 65,000 mark. And since SIO's checksum is essentially a simple 8-bit carryover checksum, you're going to get a lot of repeating values once you get above 128 or 256 bytes or 512 bytes of a data payload for that checksum to really be meaningful or any sort of a measure of integrity. So keep your requests short, but I do provide a 16-bit value here so that you can do, say, 512 bytes, 1024 byte packets if you need to. We have a byte here for connection status. Essentially, are we connected? Are we not? Are we connected to a protocol? Are we not? Or if you don't have any protocol set up, are we connected to the Wi-Fi or are we not? And finally, we have our error byte, which basically allows us to pass back the real error that happens in our SIO transaction. This is important because, as I've mentioned before, the SIO part of the operating system only sends back a handful of errors, specifically 138, which means we timed out, 139, which means the peripheral sent back a non-acknowledgement character for whatever reason, didn't understand the command was invalid, whatever. You have certain serial bus commands, so you send too few bits or too many bits, so you have underruns and overruns. But you also have what's called a device done error, which is 144. And that is really nothing more than the peripheral sent back an error instead of a complete. That's it. That's all SIO sends back. That's all it knows to send back. So we have to provide any extended errors that we want to send ourselves as part of a status request. And we're using the error byte here to facilitate that. Coming back to where we were, we can see that we allocate the errors, we allocate the buffers, we open the protocol, and if everything's good, we send back a complete. Otherwise, we send back some measure of errors here. Conversely, with close, we try to do any housekeeping that we need to do. And in each one of these, it's important, especially because this is production firmware, we need to program defensively because we're using pointers for dynamic allocations of protocols, and we need to protect against null pointer errors. Boom, just go back if it's not there. Otherwise, we send a close command so it can do any housekeeping that it needs to do, send back the complete. If it fails for whatever reason, we send back an error. And then we finally delete the protocol object, set it back to null, deallocate any buffers, boom, Bob's your uncle there. The read and write commands are pretty straightforward too. Again, we program defensively, checking for null pointers. And if we have a null pointer problem here, if the protocol isn't set up, if someone sends a read command before an open command, we need to check for that and trap that and say, well, we're not connected to anything. And that's essentially what the 128 is here. Otherwise, we go ahead and do the read, passing in the receive buffer and the contents of the command frame here, which correspond to the number of bytes that we want to read. That's our length. Finally, once we get that back from the protocol here, our buffers and our lengths here, since we already know the length, we just pass that back. Bam, bam. And honestly, I should actually take this and put this here too. Something for later. Just more refactoring here. Same thing for write. Program defensively. If they try to use write out of sequence, we're not connected. Bam, done. Otherwise, we take and get the data from the computer, set the appropriate lengths and buffer sizes, use the protocol command to write that out to our target. Done. The special area here is our status. Now, I'm still debating on whether or not to have this particular portion here or not. I put this here as a matter of programming defensively, but ostensibly because I'm still trying to figure out the best way to handle this. So right now, basically, if no protocol is defined, that means there's no connection on this particular device, then we just simply return whether or not the Wi-Fi is connected or not. Otherwise, we take and call the protocol's status command here, passing in our status buffer that we're ultimately going to send across back to the computer. And again, the special here, we check for a valid command, bam, make sure that we're actually connected. If we're not, bounce back. Otherwise, we do our special call here for a protocol, and we can see our individual SIO commands here, bam, process. If we dig into Network Protocol TCP, we can see the guts of the TCP implementation. Again, this is the part that actually does the parts that interact with the individual protocols themselves. And in this case, since we're dealing with TCP, Arduino provides the Wi-Fi client and Wi-Fi server classes specifically for dealing with TCP sockets. And these become wrappers for those functions. Our job and our responsibility here is to make sure that everything is set up for this to just work. Now, since we're passed in the entire network device spec, we can take and parse this as we need to and do what we need to do. For example, if our path is actually empty, then we assume that all we have is a port and that we need to create a server object to listen on so we can accept connections from the outside world on that port. So we set up a Wi-Fi server with that particular port, say that the connection is indeed a server, come back. Otherwise, we go ahead and do a client connect. And then we do a little bit of defensive programming here to make sure that everything is okay. Otherwise, we say the return is false, and we return back a client error code of 170, which is essentially the connection did not work, or the listening bind didn't work, something failed. And we can present that to the user as, well, we weren't able to connect, or we weren't able to establish a server connection. Now, a side note to that, because the Arduino functions themselves, client connect and whatnot, don't really provide us with any interesting information other than a simple integer that says either true or false as to whether or not a connection was actually able to be made, or basically that a server object is returned. We can't effectively debug down further into the nature of why something failed because they didn't provide a way to get an extended error code out. So if we want to take and get more information, we're actually going to have to dig down into the IDF and pass in the file descriptors that these objects are working with to try and get more information. And that's something I'm looking into now. Close, again, some housekeeping here. We stop the connections, which cleans everything up for those particular connections. The destructor will take care of removing those objects, so we don't have to worry about that here. We have the read, again, defensive programming, where we figure out, okay, are we connected? If not, say we're not connected. Otherwise, we return back the number of bytes read or written to, and since these are pointers, the receive buffer will have our information as a result of this read bytes call. And we just kind of do a quick check, okay, true or false. Is this, did we get a successful read or write here? Since that's ostensibly all we can deal with on the other side. Again, with the write, similar pattern. Check if we're connected. If this gets somehow makes it all the way up to here, then we pass back an error. Bam. Otherwise, we do a write. Bam. Boom. Done. The status is interesting because at this point, if a client is connected, then we have access to the client object, and we can see how many bytes are actually available. And again, since this is a 16-bit value, we're taking and spitting that into the correct byte order here for 0 and 1. And 2 now gets overloaded with what is the client still connected or not. And finally, status buff 3 winds up being our client error code, which gets set whenever a read or write actually fails or not. And you can see that up here, you can see that being set here, you can see that being set here, etc. Finally, we have special handling, and the only special code that we're currently handling right here is just for accept connection. There will be more, but this is the first one here, just to take and accept a TCP connection. Boom. And again, accept the connection. Defensive programming, make sure everything's right. Otherwise, we take and accept the connection, move on. So that's essentially the implementation for the protocol here. Now, from the other side, we also have the test programs themselves. Give me a moment to actually make it over to this window. And if we look, we can see that we have our repo here, and inside that repo we have nhandler. Inside that nhandler we have test programs, and we have test programs for the SIO side of things. Looking, we have individual test programs for each of these particular file operations that you see in network.cpp. For opening, closing, reading, writing, and status. And there will be one for special. I need to go ahead and write that one soon, once I get the rest of these debugged. The implementation of these programs is very straightforward. Since all the logic is actually handled at the ESP itself, there's not much that these programs actually need to do except form the request in the right way and form the request in the right manner. And because these particular programs are using the device control blocks for SIO directly and calling SIOV directly in the operating system, they do not need a handler. So if you want to write a program that just uses the SIO functions directly from FujiNet for reading and writing to the network, you can. And you get the advantage that you implement the functions that you need, and you're not, and the amount of memory that would normally be taken up by the handler ostensibly could be better used in your program as you see fit. So this is your option. We can see right here that we pass through as part of our call here our open command. This is a write, since we're writing a path to open back to the peripheral. It's a buffer of 256 bytes, and we pass through the aux1 and aux2 parameters as we get them on the command line. Again, we do our usual error handling here based on the return of the error that gets sent back, which is one of the error codes that I described earlier for SIO, 138, 139, 144, etc. And then if everything's good, we just say, okay, open, sure. Since this particular program is a command line program, it actually has a series of options that will be printed if you don't provide the correct number of arguments, with some examples. We check for it, everything good, okay, great. We copy everything into the buffer, and finally we do our inopen call. There is an additional branch here specifically for DOSes that don't have command line parameters, so that we can enter those parameters in interactively. Conversely, you've got bits and pieces like the enclose, which again, you'll see that we're using device number 7.1, which corresponds to the first in device. 7.0 is reserved for FujiNet control, so 7.1 through 7.8, which corresponds to N1, N8 on the CIO side, are reserved for network operations. And those devices will respond to those commands from here. You saw the one for O, this is for close, and since we're just closing the connection, we're not really expecting any parameters, we just simply do it. Simple enough. For read, we go ahead and specify in a number of bytes to actually read from the socket, which corresponds on the other side to the aux processing that you saw in the protocol for reading and writing to the TCP socket or UDP socket. Pretty much the same either way. You have to know the number of bytes you want to read in advance. This is why the status call is so important. It goes, does it, displays the result, and the same usual argument processing here. Grab a length, etc. In write, much the same thing, but instead of read, it's a write with a corresponding write to dstat_s, pointer to the buffer. Bam, it's written. The thing here is that there's no command line arguments. I opted instead to basically get the data from the user each time the command is actually written. And the reason for this is actually because command line options in OSA+, DOS-XL, Sparta-DOS, etc., the command line DOSes that support parameters don't take long strings all that well. So I just bypass that particular problem. And as you can see here, up to 255 characters can be pulled in on a line. It's using the E device, the editor device, to actually do that. In the status, we can see here we have our status command. It passes that, puts that into the part of the operating system that we have, part of memory that the operating system sets aside for status requests, which are 4 bytes called dvstat, which begin at 746, decimal 746. So we grab those, display them out, and of special note here, we have an error handling here so that we can show some of the errors that can possibly happen. And you can see these correspond to the error numbers that are actually in the handler here on the FujiNet side. So all of that's pretty much handled. Is there any other I didn't get to? Nope, that's pretty much it. Finally, you have a makefile inside each one of those projects, a makefile out here which takes and builds all of those projects, as well as a dist command which takes and builds all these into a disk image, which can be copied over to a TNFS server or onto a flash card, whatever, just any SIO device for testing, so we can run these programs and test it. I've already done this, and we're going to take and use the next part of this video to show the output of these commands and what can happen. So with that, we'll go ahead and turn on our video output. And I'm going to go ahead and reset the FujiNet here. Gotta love high speed. And we're going to use, from my SD card, I'm going to go, since we have folder support now, my display output is much cleaner. I'm going to use OSA Plus 2.1 for this part of the test here because it's a nice command line DOS that doesn't get in your way too much. Start here, go here, great. Mount it read-only. And I've copied the tests over to my TNFS server here. We'll go ahead and select them. Again, mount this as read-only because we don't need to write to it. Mounting this read-only has the advantage that a file lock isn't attached to the file, which means if I make a change over here, I can, over on the PC side of things, I can copy that over. I can take and make a dist. You can see the individual programs actually being built here. And again, this is being done in CC65 because C is the language I'm most comfortable with. I have no problem, all of this, because I'm only using operating system functions here, all of this could just as easily be written in BASIC if you wanted to. It doesn't matter. So we have our in test. If I could just as easily take and copy that over into C drive Z here. And in fact, let me make sure that that actually is still mounted. I have rebooted this machine in the last day or so. Yep, there we go. Yep, mount that over. Bunk, excuse me. Apologies here. There are windows. I have windows that I'm doing stuff in that you cannot see. But that's okay. Come on. And you can see I'm copying that over. Okay, great. Boom. And I can instantly see the results from the Atari side of things without having to reboot. So we'll go ahead, that's mounted. We'll go ahead and hit Option, hold down Option to disable BASIC. And you can see this is my version of OSA Plus that has the FNC tools on here. You can see my network configuration there, so I can have access to the host name and any network particulars for my testing. We'll go over to drive 2 and we see our testing tools right here. So for this next piece of the test, I'm actually going to start up a copy of Netcat. And we're going to open up a listening port on port 6502. Now it's listening for a connection. If I go ahead and run inopen, you can see that since we're in a CLI DOS, it's giving us the argument list here so I can put it in. And you can put a host name, again, you can put host names here, you can put an IP address here. Does not matter. And I need to specify auxiliary bytes. Since I'm not parsing these, they're not really used by the handler at this particular point in time, so I can just put 0 here. Doesn't matter. And you can see that the connection is actually opened. If I go ahead and use in-write, there are no command line options here. It's just asking me to enter in some data. We'll go ahead and hit return, and we can see that the output instantly shows back up at the PC. If I do it again, and we can see that this is happening again. Now you see a particular artifact here. This is showing me that I need to take and clear out the buffer each time that this write actually happens, because we're seeing the second string that I sent was just a little bit smaller than the first string that I sent. Okay, so this is the reason why I'm writing these individual test programs, to ferret out these particular bugs early on in the process. Conversely, if I go ahead and send in if I send in some input here, since Netcat opens up a connection to the other side as well, if I send this over and then do a status, we can actually see, ooh, we have a particular error here. I have to see what happened here. But we see that there are 8 bytes actually waiting in the buffer here, and that we are indeed connected, because we are connected as one. Okay, great. Well, if I go ahead and read that out, we can see that it came back. And if you heard close enough, you actually heard that little click, click, and that's because it sent the command twice. And in fact, if we actually took a look, I don't think I have the monitor set up here from the other side, but if I, and I do not, you would see that there was actually an error sending that command for whatever reason, and it resent the command again, and it worked the second time. This is something I have to investigate. But you see that the values came back. Great. So fantastic. Finally, if I take and close the connection, you can see it disconnects everything, and everything's okay. Now you can see this a bit better if I take this, remove the -k, which keeps the connection alive, and do the connection again. You can see that happening there. Bam. Okay, great. Finally, if I take an enclose, you can see that the connection closes, and we go back to the command line here. Conversely, if I go ahead and open now, since the Netcat is no longer running, you can see that it will attempt the connection, and it will ultimately fail. We'll get back an error that we're supposed to actually see and decode as the 170, which is not found. The connection was not successful. Something happened. The reason that this command is so coarse, literally, again, comes down to the fact that we don't have any meaningful return information from the connect command that ultimately gets sent by the underlying IDF framework. That doesn't get bubbled up to Arduino, because Arduino has no facilities for handling that. It's just a blockage of information. So that information becomes opaque. There's still a bug with passing back status information, because if I take and do an end status here, you can see that our net status is all zeros, and it says that it's okay. This is not correct, and I need to see why this is happening. Still more to do. But we'll go ahead and enclose anyway. Close everything off, and there we go. I'll end this particular part of the demo here by showing what this looks like under DOS 2, and for that we'll take and hit the reset. And look at this from the other side. Go ahead here. I'm going to go ahead and turn on the display here and go back to my VS Code window. And we're going to open up a monitor connection. Miniterm is running. Let's go ahead and reset the device. We can see this happening here. Okay, and I'm going to swap out my copy of OSA plus 2.1. I'm going to swap that out for a copy of just plain DOS, Atari DOS 2.0. So there we go, looking again. Here's our tools ready to go again, so I'll go ahead and run device spec. And finally, I'm going to make absolutely sure, going back on the other side here, that I'm actually have my netcat running. And oops, something happened there. Looks like there's a crash that I need to debug. Whoopsie. Yep. Okay. So protocol, TMA, path. Ooh. Looks like we've got an interesting issue happening here. Okay. So looks like the 0. That is interesting to say the least. Looks like some bits and pieces that I have to take and debug here. So again, this was kind of just a status report to show where things are at this particular moment in time, and it's fine. So it's like as I've said before, still some more to debug, but I wanted you guys to see where I was at this particular point in time. So I'll go ahead and end the video here. So going forward, my tasks essentially are to get all of the low-level bits and pieces debugged, prevent crashes like what you saw here, and to make sure that the errors that are reported actually get bubbled up to so that they can be picked up by the CIO layer. From that point, once I know that all of that is working like it's supposed to and in spec, I can begin to fix the CIO handler, make the CIO handler work better, and debug it in earnest. And at the end of that, we'll have a functional end device that I can take and demonstrate to you guys. This is the muck of the whole project, and the difference between making a series of test programs versus making making the individual proofs of concept and making the production firmware. So with that, I want to thank you guys for sticking with it this long here, and until next time, have fun.